talk about today is try to move the context from UK to Scandinavia and talk a little bit about population structure and migratory patterns. So I will talk a little bit about sea trout abundance, focusing on Sweden, but also talk a little bit about Norway and Denmark. Also mention a little bit about population structure. We have done some genetic works. Main focus will probably be on migratory patterns and mortality rates on the outward migration. And I will also talk a little about the various approaches we have to model abundance. And then I will also give a plug for the ICES working group, Viggo Trusta, to end with. But since it's an early start, I thought it could be nice to start with some nice pictures of our small streams on the coastline of Sweden. So this is a couple of pictures that shows how it looks in the sea trout streams on the western coast of Sweden. So as you can see, they are very, very small, and most of the streams doesn't produce fishing opportunities for sport fishermen. This is mainly juvenile habitats, but they are very, very productive. And as you can see, the influence of riparian zone is really, really crucial here. That is really what triggers the productivity in these streams. So you get to long for the summer when you see these pictures. Just in a few months' time, this will start to grow. So this is really great. So all these streams is within 1 hour of traveling from Gothenburg, where I'm positioned. So it's very neat to have these field sites in the nearby region. So this is what we consider a good habitat, with a lot of material from the riparian zone falling into the stream, a lot of breeze blocks, a good habitat both for juvenile spawning areas and also for juvenile holding position places. This then, we need to figure out how do we monitor abundance in these streams then. This stream on the left is actually the same stream in high flood and low flood. So the stream really changes. So it, of course, then makes it dramatically different if you want to go electrofishing in different opportunities here. All these streams feed enormous amount of sea trout, and the sea trout is now the main target for sport fishermen along the coastline. So this is really crucial that we try to monitor it. So this is popular sport fishermen. The main way we do abundance for sea trout in Sweden is by electrofishing. We have covered almost all of Sweden in electrofishing localities since the 70s. So we have a quite unique data set here. In total, there is approximately 800 sea trout streams in Sweden, and they're all dominated by these fairly small streams. On the east coast, we have some larger streams where they stock hatchery trout to improve the stocks. But on the west coast, where I'm positioned, it's only naturally produced sea trout. So if we then look at, based on this electrofishing data, what have this given us and how has the development been? So this here is the average amount of trout, 0+ fish, abundance of sea trout par, and this is the deviation from that average. So if the figure is above that line, it was better before, and if it's above, then it was worse before. So you see a trend line here coming from 95 to 2014. And also, since Sweden is a very tall country, there's big difference in the climate. So up north, we have an average temperature of -2 to 2, and south, 7 to 8 degrees, the sort of yearly average. So we need to divide that up. So what that gives us is that we have a development in sea trout par population that's positive in the north, but unfortunately seemed to be negative in the south. And that was a little bit worrying because we really don't know what that means and why that is the case. But if we then start to look at the recruitment of different year classes, we can see this is only then from the west coast, that we have a steady recruitment of 0+ fish. Older than 0+ fish seems to be decreasing, but on the other hand, the size of the 0+ fish is increasing, and the smolts seem to be decreasing in size. So this seems to be sort of a familiar story about that. We heard that several times yesterday. So what we expect here as well is that we see an earlier smolt run. And we have some data to support this as well. This is from Headwater, just south of Gothenburg. And the open circles here are older trout, and the black bars are young-of-the-year trout. And we can see that we have a steady recruitment of young-of-the-year trout, a decline actually in the older trout, but at the same time, we have an increasement in the amount of smolt that leaves the system. So this gives us also suggested that we probably have a larger proportion of 1+ smolt that leaves the system. So hopefully then that means that we still can keep the fishermen in the sea happy. But we don't show really, we need to sort of consider and follow this up. So what will really happen? We have an increased growth, we know that. The increased growth will make the par larger. Seem to be as the smolts will be smaller and more. We don't know really what are the possible consequences of this in the long run. So this is something that we need to both monitor and model. There might be that we have high survival and growth of this fish. Could be that they return earlier as a zero-winter fish. Could also change the survival and competition. So there's all different scenarios that we really don't know what will happen. So this is crucial that we try to follow. So just some quick words about the situation in Denmark. Here there is an average about 400 sea trout streams, so there's still a lot of sea trout streams here as well. The densities of 0+ trout has increased, although there is a larger regional difference here. But this is the overall smolt productivity, and it's estimated to be 600,000 smolt produced here. Norway, unfortunately, has very, very little assessment going on, and they started much later than what we have done. They have approximately more than 1,100 streams with sea trout, so maybe they have so many that they think that it would be enough. But unfortunately, the catches has really declined. So in the rivers with permanent fishing, there has been a decline by almost up to 3/4 in some areas. So that's a big concern as well. Right, so now I'll move a little bit on to the population structure. All these streams in Sweden, they are assumed to be more or less genetic unique, but it hasn't really validated. So we wanted to see to what extent do the fish really return to their home river to spawn. So to do that, we did a genetic differentiation using single nucleotide polymorphism, SNPs, as a tool. So we collected 500 fish from 22 different fish, and this was spawning fish, so we knew that they were returning to the rivers to spawn. And we did sport fishing samples on 64 fish, sport fishing, angling, caught fish. So this is the coastline, and this is the number of streams that we work on. And the suggested population structure here that surprisingly, there wasn't 22 different genetic strains. It seemed to be clustered into mainly 4 main structures. We had one northern group, we had one southern group, and one central orientated group. So this suggests that the sea trout in this region are probably not adapted to their home local river, but whereas more likely in fjord areas or larger systems. And that could also explain why it's so easy to restore these kind of habitats. It can be shut down for decades, but the moment you open up a barrier, you have sea trout spawning the same autumn. So the straying is probably quite large in this system. Just a word about this Söron, which seems to be special in a way that it is attributed to one of the largest streams, and it seems to depend completely differently. So the take-home message here is that the local adaptation seems to be fjord areas. And this is the trout from the river Söron. And if I would show you this picture, you would of course say that this is a female and this is a male. But that's not the case. This is 2 females. And clearly this fellow here is this group here. So that's completely genetically different from the rest of the trout here. So this is something that we want to look into. And they spawn in tributaries to the largest river we have. So maybe they don't go out into the sea at all. We don't know, but this is something we want to follow up on. Right, so where do the fish go then? What is the migratory patterns? We've done some studies on this using hydroacoustics, pit tags, and data storage tags. Try to sort this out. The study area, again, on the west coast of Sweden. 2 systems just around the area of Gothenburg. Byfjorden just north and Himlån just south. Starting with the largest experiment we'll be doing for 2 years, using Himlån as a fairly large river. And the first thing we wanted to do is to investigate the triggers. What is the triggers for out-migrating fish? And also how much fish is actually produced on the outward migration here. So for that purpose, we had a smolt trap for 2 years, and we've emptied it every day to see when did the fish go. And then we had a number of logging stations. This is the picture where you just saw from the river. A couple of receivers here using the Demco system, and then it's a big estuary here where cormorants, Niels's bird, is occupying, and also a number of receiver rows in the coastline here. So we could follow them on the outward migration here. So the triggers then seem to be both discharge and temperature. And this shows really that it's crucial to repeat an experiment during 2 years, because the results were quite different between the years. In 2011 was a very unique year in the sense that it never rained. The temperature just increased, and there was never any peak in discharges. And of course, that forced the fish to move. So around 10 degrees, this is the discharge. As you can see, the discharge just dropped. But approximately around 10 degrees, then the fish started to migrate anyway. So they had to leave the system. In 2012 then, was a more normal year. And you can see at every peak of discharge, here is one, there is one, there is one. You have also a peak in the out migration. So clearly the triggers for outward migration differed between the years. Seems to be that discharge is probably the main driver, but when you come up to 10 degrees, too costly to stay behind, and then you need to get going. We could also see that the temperature increased the proportion of day migrants. So at the temperature of 10 degrees, this is the proportion of night migrants, but above 10 degrees, you have a larger proportion that start to move all the day around. So they could also be costly in a way. So the take-home message for this, I think that when we see that our streams get increasingly fragmented, it could alter the discharge and also the temperature. So they could also change the triggers we see for outward migration. So we need to bear that in mind. We could also see, which I don't think has been reported before, that during this outward migration, salmon and trout were quite often using shoals of roach to migrate in, to sort of probably avoid being eaten. So quite often seen in these shoals. So then we continue to follow them on their outward migration using these acoustic transmitters. And as I mentioned, there was a huge difference in the discharge between the years, and that also was reflected in the difference in mortality. At the year with low discharge, we had the mortality rates of smolts of 51% and kelts and 30%. And in normal discharge, the mortality rate was down to 26% or 5% for kelts. So twice as much increase in mortality in low discharge event. So clearly that's something that we need to bear in mind when we try to model the mortality rate, that it can vary to a large extent really. Then we follow them along the coastline further out, and we could see that it's mainly, this is from the inland shore and to the outer coastline. And this is clockwise activity. So mainly nocturnal migration on the migration route towards the coast, outer coastline. But when they are on the outer coastline, they seem to be feeding more happily around the hours. We don't know what they're doing, but we interpret it as they probably start to feed in this region, and they are just out migrating to feed in this region. We could also see that the migration seemed to occur in 2 clusters. So they don't migrate, even if there was a discharge event forcing the fish to get away, they seem to be holding back some of the population. So what I'm going to show you now is a small animation. So this is a sketch of the area. This is the receiver station in the stream. This is the estuary, and this is the receiver line on the coastline. And each dot you will see will be an individual fish moving outwards of this region. And the animation isn't 100%. They don't move over the island. They go, of course, they go around the island. But what I want you to see is that some fish really stay behind for quite a while, and some fish just disappear straight out of the coastline. So it seemed to be two main clusters. One fast leaver, goes quick out of the system, and one that stays behind and utilizes the stream to a larger extent and also stays in the estuary for a longer period. So that's what this figure shows, that you have these two main clusters. So that will be the take-home message for that telemetry, that you have two types of migratory clusters, one that goes very quick and one that stays behind, and also that you mainly have nocturnal migration in the river system. We did a similar thing up in Uddevalla, which is north of Gothenburg, where we had two rivers coming out of the system, and we tried to follow them on the coastline here. This system is very different. The further study was doing where we have a very, very shallow water and a huge estuary. Here, the fish has to enter immediately into quite deep water. So this is a fjord area. So we would expect that the mortality rate would be slightly lower here. Again, we saw the same pattern on migratory clusters, that when you had an increase in discharge, a lot of fish left, but not all. This is April and this is May. So again, you see fish leaving at a discharge event, but not everyone. So two different clusters. And the early one also seemed to be staying longer in the inner fjord. And the one that migrated earlier, they also seemed to disappear out of the fjord earlier. Probably sort of more prolonged migration on the coastline, which we don't know. So this is just to give you an idea about the survival rates. They were generally high in streams. There were no difference in the survival rates. So usually around 80% in one of the streams and 70% in the other streams. So it's a fairly good survival rate still. And this figure is just to show you that most of the fish turned the northern direction and some went in the southern direction. The different colors here just refers to the different streams here. So we could follow them on the outward migration. But still, we only could follow them to this spot, and then they were lost for us. So we also had done some work on data storage tags, where we tried to see what kind of depth are they using and how much time do they actually spend in the sea, and do they go up and down. So for that purpose, we tagged adult individuals using these data storage tags. We tagged them in the stream. And then the idea was to let them go out into the ocean, and then we should hopefully recapture them the following year in the stream again. Of course, this was a high-risk project because we need to get all this back. So we got a number of fish back. So you can clearly see here that you have a number of events where they dive down to 8 meters, to 10 meters, but most of the time they are sort of surface feeders. So it gives us some idea. Out of these 22 fish, I think we have recovered 6 at the moment. None in the stream, unfortunately. They've all been recaptured by people walking their dogs, finding these pieces on the shore. Most of the fish has ended up in this way. I don't know if you can follow the pattern here, but this is the temperature that drops to this level, and then it decreases to 40 degrees. Yeah. You just mentioned it, yeah. So 5 out of these 6 tags ended up in that way. Right. Has anybody got the time, so I'm not talking too much? Are you okay? I'm okay. Good. So now I want to end up with a sort of a little bit of talk about how do we use this electrofishing data to assess the smolt production. So we have this huge amount of electrofishing data, and there is also quite a lot of habitat surveys by the county boards down in Sweden. So we try to merge this technique to sort of model smolt production. So what we need then is we need some sort of quantitative habitat classification. We need electrofishing at representative habitats. We need to assess mortality, degree of smoltification, migration mortality and winter mortality, and also some sort of region-specific data. Since Sweden is a very tall country, we can't use just one data. We need to have region-specific data that differ from the southern region to the northern region. So this is one way that we can sort of model our abundance, that we have electrofishing, we calculate age structure, we assess the habitat class, and then we estimate all these parameters, biotop mapping, winter survival, and all other factors like chemical and physical parameters. So it can get quite complicated, but in the outflow here, we should have sort of a calculated smolt production. And this has been done in some streams where we try to validate and test this model. So I will just guide you through some examples here. So what we've been doing, we've been dividing up the stream in a number of categories that gives us an idea about how suitable all this habitat for trout. And that goes from class 0, that's unsuitable, to class 3, that is a good, very good habitat with good substrate, velocity, shade, and complexity. So that gives us sort of the top score. And then we have region-specific average densities within each of these habitat categories. So this is, for example, in Vättern region, in the middle part of Sweden, habitat class 3, 0+ fish should hold 97.3 0+ fish per 100 meters. So that's sort of the average that we use. And then if we extrapolate on this, we know that this should be 100%, and then in habitat 1, we should have 57% out of that number. So we can then use this data to extrapolate for different habitats. So that could be a way of sort of modeling it. So then we walk through the whole stream, and we do a definition of stretches, and we do habitat scoring, and then we have electrofishing at some representative sites. So that means that we don't need to have data on all of these categories. We can then just extrapolate it if we know to some extent where the qualities are and what are the numbers in some of these categories. So this is one example that we've been walking in the stream and categorized. This is a good habitat, 3, 2, 3. And then you get an idea about the distribution. This is an example of class 3. This is sort of the top-ranked habitat. So this was definitely be scored as class 3. And on top of this, then we add electrofishing then at the representative habitats. We need to add winter mortality, degree of smoltification, migration mortality. And as you can see, in the poorest habitat, we have a mortality rate of up to 17%. In the best habitat, between 0 and 5%. But then we need to add this fellow as well, the lake mortality. And that can, in some data, it has been supported up to 75%. So it gets quite complicated, but we need to add the lakes as well. So there's a number of literature data, but there's much more data that we need to put into here. So clearly, Sweden has 4 index rivers and 3 with small trap in Norway. So we need to see if we can use this small trap to validate the system. And in River Ävån, on the east coast of Sweden, this small production has been quantified in 8 years. The average deviation from those predicted was 16%, which is pretty good over a period of 5 years. But if I told you the story in the rest 3 years, it's a little bit less. So it's between 90 and 360% in the remaining 3 years. So it's a huge variation there, of course. But still, in the old run, you could probably see that there is a trend that it could work, sort of prioritizing tool, and to some extent at least. It has also been validated in Kävlung, and the accuracy here was between ±25%. So it's not sort of a rocket science tool, but it gives us an idea, and when we want to start to prioritizing where we should do a restoration effort, that can give us a guideline here at least. You can also have a simpler model where we just base the system of a number of fixed percentage of its density, and then has a mortality potential of this. And that's been done in Himlån, where the migration mortality probably is higher. Here we added production from 30% abundance of the 0+ fish. And then we add a mortality rate, and this resulted in an overestimation between 18 and 90%. So it's still acceptable, I would say. It's not sort of really that good, but when we sort of try to improve the data we put into, I think that we can even get better results here. Right, so I would try to just sum up a little bit with some conclusion. I think that we need to say that the sea trout stock in Scandinavia needs a more standardized assessment. It's very sort of vague and diverse at the moment. The development of stocks is positive probably in Sweden and Denmark, but more vague and questionable in Norway. Due to the catches, this might be a bit threatened. Genetic clusters that we found suggest that we have a large degree of strayers. We probably still see homing, but the data suggests that at least 10% ought to be straying. The triggers for auto-migration seems to be both discharge and temperature. Migration is mainly nocturnal, and mortality can indeed be substantial, especially in years at low discharge when the trout has to go through estuaries. Temperature might also change the timing of migration. Biological reference point is missing to a large extent, and we need to add them along this north-south gradient in Sweden, and also going further down in Europe. Stock assessment based on this habitat mapping is possible, I would say, but we need to have longer time series. An alternative simple model needs to be developed and evaluated, so that's what we start to work on at the moment. Parameters such as winter mortality and migration costs needs to be further validated and tested in different systems. An accurate model will help us to manage a system. I think I've shown you now that the model work to some extent. It won't give us the exact number, but will help us to prioritize our activities. And it could also help us to maybe highlight and know exactly what would be the effect of various kinds of restoration activities. So this is some examples of sort of habitat restoration. So if we know then the effect of improving the gravel bed or improving the structure for large fish, then we could hopefully get an idea what would happen for the small productivity. So that's done in both small and large scales. Right, so the take-home message is that the habitat modeling can act as a guide on which sections to restore and a little bit on how. Right, so that was the last slide, and then I just want to acknowledge a number of people that are working with this. This is Anton Halldén and Niklas from Jönköpings Fiskeribilegård, and also David Alvén, who's been my PhD student. He's been done most of the work regarding migration. So before I start, I would also like to do a small plug for this part here. Is that okay? Absolutely. Yeah, perfect, thank you. So in your package, there is a leaflet with some information for this working group. And there's been two workshops on sea trout. And the last workshop suggested that we need to get going with a working group with the overall aim to develop these assessment models and also establish biological reference point for sea trout. And we all heard a lot about the complexity of the sea trout, so this can be tricky. But ISS accepted the proposal, so now this working group has started. So it will be chaired by me and Alan Walker. And we will have the first meeting on the 24th to 26th of April in Gothenburg. And I also want to highlight that this is not a workshop, there will be a working group. So this will be a starting point. And then they will run over 3 years. And the overall aim is really to try to develop these models and also to provide a database. So the first thing we want you to think about carefully is, first, of course, you're more than welcome to join us in Gothenburg. But if you can't join us, please think about, sorry?
Let's say data, yeah.
Yeah. Data, yeah. Data wanted, yes. Because I know that I talked to people here and you have provided important data. So I think one of the ideas with this working group is to provide a database on data such as juvenile densities, habitat characteristics, abundance of spawners, out-migrating smolts. And the idea is to give this in a transparent database so we all can access it and start to work on different approaches and model it. So we will, of course, think about how to access it, but the idea is that even if you not join us in this working group, you will still have access to this data and try to sort of get a transparent use of it. So I think that would be neat. Right, thank you very much for your attention.